Review video number 1, capacitors in series and parallel. Which capacitor stores more charge Q and has a larger potential V across it? We want to recall that the definition for capacitance is Q over V. And therefore V, if we solve that, is going to be Q over C, which we might need later. But these two capacitors are in series. And when they're in series, capacitors store the same amount of charge. The one that has a larger potential across it, if we look at this equation here, if they have the same amount of charge, Q, but this one has a larger capacitance, which means the voltage across it is going to be smaller. Same amount of charge divided by the larger capacitance is going to give a smaller voltage. The same charge divided by a smaller capacitance is going to be a bigger voltage. So I'm thinking the one that has the larger potential across it is going to be capacitor number 2. So let's figure out all these quantities. All right, how about the equivalent capacitance, which is the capacitance that we should put in there if we tore these two out and just put one capacitor in their place. These capacitors are in series. You have to use the 1 over rule. 1 over 18 plus 1 over 9, add those up and then take the reciprocal, and that's going to give us 6 nanofarads. The total amount of charge is always equal to the equivalent capacitance for the whole circuit multiplied by the voltage of the battery. That's going to be 6 nanofarads times 6 volts, 36 nanocoulombs. That's the total amount of charge. Since this circuit, there's only one loop, that means that the total charge on capacitor number 1 is also 36 nanocoulombs and 36 nanocoulombs for capacitor number 2 as well. Capacitors in series have the same charge. All right, now when we were doing circuits, we talked about using colors to help us understand that certain sections of circuits are pressured up to a certain electrical potential. And we said that all of these regions that are the same color, I like to call that 0 volts of color. Well, this portion in the middle here that's shaped like an I for Illinois, go Illini, we don't know what that voltage is quite yet. All right, but we can find it, I think, because voltage, let's see, what's the equation here at the top? The voltage across a capacitor is going to be the charge on the capacitor divided by the capacitance. The charge on the capacitor is 36, the capacitance is 18, so I think across capacitor 1 we have 2 volts, and across capacitor 2 it's going to be 36 divided by 9, which is 4 volts. The pressure of this wire right here is 4 volts of electrical pressure. And does that agree with what we said up here at the top? We said that capacitor 2 should have a larger voltage, and it does. See, 4 volts, and across capacitor 1 is only 2 volts. All right, so the energy stored, there are any number of equations we can use. My favorite one to use, because it doesn't have any exponents, is 1/2 times Q times V. If we take Q times V and 1/2, so that's 1/2 times 36, so that's 18 times 2, so that's 36, and then the nano prefix hasn't canceled, so 36 nanojoules. And then for capacitor number 2, the energy is going to be 1/2 times 36, so that's 18 times 4, which is 72 nanojoules. The total, you can find it 2 ways. You can either add up the energy from both capacitors, which is going to be 108 nanojoules, or, and this should work too, I hope it does, you can find the total energy by using this same equation, 1/2 Q total times the voltage of the battery. Does that work? 18 times 6, boom, 108. Let's do another one. These capacitors are in parallel. Which one stores more charge? Yeah, you know what? I'm going to skip that. Let's answer the one about the voltage. The voltage is going to be the same, isn't it? Because when you color code these circuits, that whole bit has the same voltage. We might say it's 6 volts of pressure. The pressure of that is going to be 0 volts. Why make it complicated? Just call this one 0 and call that one 6, because the battery says that the difference is 6, so let's make it easy on ourselves. Which one has the larger potential? It's a tie. And what's the equation? C is equal to Q over V, or Q is equal to C times V. So if they have the same voltage, then the one with the larger capacitance will have more charge. C1 is going to have more charge there. We've already figured out these voltages, haven't we? The voltage across all these elements is going to be 6 volts. Right away, we can fill that in. 6 volts, 6 volts. The equivalent capacitance, these capacitors are in parallel, which means we simply add up the capacitances. 27 nanofarads. The total amount of charge that is going to be moved in this circuit is going to be the equivalent capacitance, which is 27, multiplied by the voltage of the battery. So that's 27 times 6, which is going to be how much? 162? 162, I believe, nanocoulombs. What about the charge on each of the capacitors? Well, once again, charge, you can see at the top of the screen there, Q is C times V. C times V. For number 1, that's going to be 18 times 6, which is how much? 108 nanocoulombs. And for Q2, it's going to be 9 times 6, which is 54 nanocoulombs. Does that add up to 162? It does. Look at that, 162, just like we said. We said the total amount of charge would be 162, and it is. Okay, excellent. The energy is 1/2 Q times V, so that's going to be 1/2 times 108, so that's 54 times V1, which is 6. So 54 times 6 is going to be 324 nanojoules. And how about this one? This is going to be 1/2 times 54, so that's going to be 27 times V2, which is 6. 27 times 6 is going to be 162. 162 nanojoules. So if we add these up, that's going to be 486 nanojoules. And just to check, is it true that the total energy is equal to 1/2 times the total charge times the voltage of the battery? So the total charge is 162, so that's 1/2 times 162 times the voltage of the battery is 6, and that's 3 times 162. Boom, right on the money.